Welcome to section 1.2. Not to put any pressure on you, but this will be the most important section of the semester in terms of computational techniques. So in the last example, in the lecture notes last time, I took a matrix that looked like this and I reduced it to a matrix that looks like this. And along the way, I encountered different forms of that matrix, and I want to give those forms names. So a matrix is in echelon form if there are any zero rows, they're at the bottom. Now this matrix had no zero rows, but if there had been any, they would be at the bottom. And then the leading entries, which are the first non-zero entries of each row, form a triangular pattern, meaning they've got zeros below them. So here's a leading entry, here's a leading entry, here's a leading entry. They have zeros below, and then each leading entry lies to the right of the leading entry above. So they form a triangular pattern, but the triangle has to go this way, going down from left to right. It can't go like this. So it has to be a triangular pattern. And so in this case, I've got A and B are both in echelon form. So echelon form is not unique. C is in reduced echelon form, and that is unique. So C requires, in addition to A and B, that the leading entries all be 1, and there are zeros below each leading entry and zeros above each leading entry. Now, don't worry about the 3, 16, 29. 3 is not a leading entry, so it can have anything above it. Okay, so let's practice just identifying matrices as being in one of these forms. So when I'm classifying a matrix, I circle the leading entries. And in this case, my leading entries have zeros below. Each leading entry is to the right of the one above. It's okay if they have to miss a step, like between rows 2 and 3, the leading entry jumps from column 3 to column 5. That's okay. So this one's in echelon form. The next one, I see a problem. Circle my leading entries. In rows 1 and 2, I've got a leading entry and then a leading entry right below it. So that's neither. That's not allowed in either echelon or reduced echelon form. The next guy, I've got leading entry, 2 leading entries, zeros below, zeros above. So this is reduced echelon. Again, this one here can have anything above it because it's not a leading entry. Next one, you think it's reduced echelon. It's triangular, zeros above, zeros below, but the problem is the triangle goes in the wrong direction. Each leading entry has to be to the right of the one above it. So this is neither. And this last guy, it's almost reduced echelon, except for the fact that there's a zero row here. Zero rows have to go on the bottom for either echelon or reduced echelon. So this is neither. It would be reduced echelon if we had switched rows 3 and 4. These leading entries have a name if the matrix is in echelon form. So if you have a matrix in echelon form, the leading entries are called the pivot positions. And any column that has a pivot is a pivot column. And this process that we're doing to get from any matrix to echelon form or reduced echelon is called Gaussian elimination. Now, Symbolab will do Gaussian elimination to a matrix. And let me just pause this and bring up an example. If you go to, I always have trouble finding it, but go to solutions and then pick matrices and vectors. RREF stands for reduced row echelon form. And so if you just pick a stock example, click go, it will put it into reduced row echelon form for you. It used to show you the steps, but now it wants you to pay money in order to show the steps. So back to this. Let's take a matrix, reduce it to reduced echelon form. I call that RE for reduced echelon. Now I've already done the reductions, but let's identify what happened at each step along the way. And I want to show you that when you reduce a matrix to reduced echelon form, there's a direction you have to go. You have to start at the top, clear out entries below leading ones, or any leading entry, working from left to right. That's called the forward phase. And that will put the matrix in echelon form. Then you're going to do the backward phase and clear out above the leading ones, and you're going to go from right to left. So first it's left to right, then it's right to left. If you're unfortunate and you start with a matrix that has a zero entry in the upper left, then swap rows so you don't have a zero. Now I could swap row 1 with either row 2 or with row 3. I decided to swap row 1 and row 3 because I saw that row 3 is every entry is a multiple of 3, and then the next step I can divide by 3 to get a leading 1 up there. So that's what I did in step 1. Then I wanted a 1 up here so that I could clear out the 2 below. So I took 1/3 of row 1. Then I used this 1 to kill off this 2. And the way I did that is I replaced row 2. Here's the notation. I replaced row 2 with -2 row 1 plus row 2. So -2 plus 2 is 0, and then -2 times -2 is 4. 4 minus 2 is 2. You have to do it all the way across. -4 stays the same because there's a 0 above, and then -2 plus 3 is 1. So now we're in echelon form. Got leading entry, leading entry, leading entry, triangular. This is called the forward phase. Now we're going to start the backward phase. So we're going to take, first of all, I'm going to turn this 2 into a 1 by scaling row 2. Then I'm going to start here and clear out above. Then I'll go here. So I'm going to go like this. Take this pivot, clear out things above it. Take this pivot, clear out things above it. So next step is to take 1/2 row 2. And these steps aren't cast in stone. You could do these steps in slightly different order. Like you might not want to scale row 2 right away. You might want to do this step first, and that's okay. So where was I? Okay, so now I've got all leading ones. Now I'm going to take this one, well, this one here, and kill this -2. So I'm going to take row 2, and replace it with twice row 3 plus row 2. And I do that all the way across. So -2 plus 2 is 0, and then -4 plus 1/2 is, I'm taking +2 times row 3 and adding it to row 2. This is why it's helpful to write down what you're doing. So 2 times 2 is 4. 4 plus 1/2 is 9/2. Then I go to this guy and I want to clear out the -2 above. So the final step is going to be to replace row 1 with 2 row 2 plus row 1. All right, and that gives me 0, 0, 10. Now the reason I have to start, when I'm doing the backward phase, the reason you want to start at the right and go this way is that, let's say I were to take this 1 and try and kill off the -2 now. So if I did that, unfortunately what that would do is screw up that 0. It would make that 0 a non-zero. So it's important to start when you're doing the backward phase at the most right column and work in the other direction. Now, I really strongly suggest you read the examples in your book. They're a little bit slow, but they're going to help you figure out how this process is done. Okay, you can do this Gaussian elimination to any matrix if you had been told this was the augmented matrix of a linear system, then this would be the answer column, and the solution to the system would be 10, 9/2, 2. But that's a big if. Okay, free versus leading variables. Each column in an augmented matrix corresponds to a variable. So for example, this is x1, this is x2, this is x3, and this is the answer column. So if that column contains a pivot, it's called a leading variable. Your book calls it basic. If it doesn't contain a pivot, it's called a free variable. So let's look at these matrices here. These are in echelon form. Let's determine who's free and who's leading. So we're told this is an augmented matrix. So I know this is the answer column, and I also know there are 4 variables. This is the x1 column, x2, x3, x4. So let's circle the pivots. Those are the leading variables. So x1 is leading and x3 is leading because column 1 and column 3 have pivots. Column 2 and 4 don't, so x2 and x4 are free. Next one, pivot, pivot. So x1 and x3 are leading, x2 is free. Okay, so let's find the general solution to the linear system, and we're going to practice leaving our answer in parametric form and in parametric vector form. And pay really careful attention to this example because I'm doing the notation different than your homework is going to do it. Mine is actually better. So I start with an augmented matrix. Just FYI, if I wanted to know which linear system this came from, it came from this linear system. You can always reconstitute an augmented matrix. So step 1, obtain the reduced echelon form of A. So the first thing I want to do to this matrix here is create a leading 1 in this 3rd spot. So I'm going to scale row 2 by -2. I'm going to take -1/2 row 2. I'm going to leave row 1 alone. So I get 1, -2, -1, 3, and then 0, 0, 1, 3. Okay, so now I have leading 1s. The only thing I have to do is clear out the -1 above the leading 1 here. So I'm going to take row 1 and replace it with row 1 plus row 2. That will give me 1, -2, 0, 6, 0, 0, 1, 3. Okay, so this corresponds to the linear system. FYI, you don't have to do this in your work, but I'm just going to point something out in the later on in the solution. So I want to show you. This says x1 minus 2x2 is 6. Read that ... as equals, and then x3 is 3. Okay, so now here's the important part. Starting with the last variable and working backwards, you're going to write down the solution in parametric form. So when I go around the room and I have students do this, everyone wants to start with x1 because that's the way we think, but you can't do that. You have to start at the bottom with x3. There's 3 columns, well, aside from the answer column, so I know there's 3 variables. You must start at the bottom. x3 is not free. So the free variables, well, there's only one free variable, that's x2. So this last equation tells me, oh, x3 is 3. But when you get good at this, you'll just read that right off of this matrix. You won't have to convert to an equation like I did over there. So x3 is 3. x2 is free. So I'm going to give it a name, a parameter. I'm going to call it t. Your book is going to write x2 is free, that sentence, which is really clunky. So if the column doesn't have a pivot in it, it's a free variable, name it. I always start with t, then I'll go to s, r, if I need more variables. Now, x1 is written in terms of x2 and x3. x1, if I read, I'm going to read right from here. I'm going to read x1 is 6 plus 2t. How did I get that? Well, remember this equation, the top equation reads x1 minus 2x2 is 6. So solve for x1, and we get 6 plus 2x2. But I named x2. x2 is t. So 6 plus 2t. This is parametric form, meaning there's a parameter in the answer. Now I'm going to write that solution in vector form. So I'm going to write x1, x2, x3 as a vector. So instead of 3 equal signs, I'm going to have 1. And sometimes it's nice just to write x bar, which stands for the vector x1, x2, x3. And then think of this as 6, and you're going to do this mentally. You're not going to write this on paper. 6 plus 2t, 0 plus 1t, 3 plus 0t. The first vector you're going to write down is the constants, 6, 0, 3. And the second vector is going to be t times 2, 1, 0. This is parametric vector form. It's really much easier to go from, to get to parametric vector form. It's always best, well, it's essential to do this first. So I'm always going to ask you for both. Okay, now what's your textbook going to do? Right now, they're going to say x2 is free, where we're going to write x2 is t. And then they're going to write x1 in terms of x2. So are we, but we named x2 t. So that's the difference right now. And then after section 1.5, your textbook is going to start introducing the vector form. So right now, they're not introducing parametric vector form. I figure we're going to use it the whole semester, may as well learn now. So what they're going to do is write x bar as a vector, but they're going to leave x2, x2. They're not going to give it a name. We're going to give it a name, t or s, whatever we have to. All right, so let's do another example. Find the general solution of the linear system corresponding to this augmented matrix. All right, this guy's already in reduced echelon form. So I'm going to start. There's 3 variables, x1, x2, x3. I'm going to start at the bottom. x3 is free because the third column has no pivot. In fact, there's only a pivot in column 1. So this is free. I'm going to name it t. x2 is also free. So I'm going to give it a name, maybe s. x1 is not free, so we can write x1 in terms of the other variables. In fact, when I read this, think of this as an equation. This equation reads x1 minus 3x2 plus 5x3 equals 1. So if you solve for x1, you get 1 plus 3s, because x2 is s, minus 5t. So when you're solving for x1 on that last equation, all of these numbers here are going to change sign when they move to the other side of the equals. So it's a -3 on this side, +3 over here. So this is parametric form. Parametric vector form is going to be x bar equal, I want my constants. So the constants are 1, 0, and 0. Then I want a vector for the s's and a vector for the t's. The order doesn't matter. You can put your t's first, your s's first, it doesn't matter. My s's are going to be, pick off the coefficients of s. 3, 1, last equation has no s, so it's got coefficient 0. And then the coefficients of t are going to be -5, 0, because there are no t's in the second equation, and then 1. That's parametric vector form. So pause the video and try it out yourself and see how well you do. And then when you come back, we'll do the problem together. Okay, so this matrix is not in reduced echelon form. So the first thing we need to do is get it in reduced echelon form. I'm going to take 1/5 row 2, 0, 1, 0, 0, 0. And then I still have to do a little bit more. I need to kill the 5 above the 1. So I'll multiply row 2 by -5, add it to row 1, and that gives me 1, 0, 2, 0, 6, and then 0, 1, 0, 0, 0. Now this is an augmented system, so I know that 6, 0 is my answer column. I've got 2 leading variables and 2 free. So I start at the bottom, x4. x4 is free, so I'll call it t. x3 is free, so I'll call it s. x2 is not free. This equation here reads x2 is 0. So x2 is 0. Top equation reads x1 plus 2x3 is 6. So x1 is 6, take away twice x3. So minus 2s, because x3 is s. Okay, now we put it into parametric vector form. X bar is my constants. So each vector is length 4 now. 6, 0, 0, 0. Then the coefficients of s, and then the coefficients of t. Coefficients of s are negative 2, 0, 1, 0, and the coefficients of t are 0, 0, 0, 1. Okay, so we'll be doing that for the rest of the semester. A couple more things, existence and uniqueness. We saw this last time. A linear system is consistent, so now we're stating it as a theorem, if and only if any echelon form of the augmented matrix doesn't have a row that looks like all zeros and then B with B not 0. So that means there's no pivot in the last column, because that equation would read 0 equals something non-zero. And then how many solutions are there? We know there's, for a linear system, it's either no solutions, 1, or infinitely many. So if you have a consistent system, you're going to have one solution or infinitely many. You'll have one solution, and it will be unique because you only have one, if there are no free variables. Otherwise, you get infinitely many solutions. So let's just answer some questions. Let A be the coefficient matrix of a linear system. If A has a pivot in every row, then is the system consistent? Yes, no, or can't tell. Yes. Here's why. If A has a pivot in every row, remember A is the coefficient matrix. If A has a pivot in every row, the augmented matrix can't have a pivot in the last column, the B column. That's because A has a pivot in every row. So you couldn't get in the augmented matrix all zeros and then a B, because you're told that these aren't all zeros for any row. Okay, next one. I love these problems. We're only going to go to echelon form to answer this question. So first, let's start with the augmented matrix. The augmented matrix for this system is 1, 3, 2, 3, H, K. Now, to get this into echelon form, I'm going to multiply row 1 by negative 3, add it to row 2. So I'm leaving row 1 alone, and I'm replacing row 2 with negative 3 row 1 plus row 2. So 0, H minus 9, K minus 6. Okay, so there's 3 cases. 1, no solution. No solution happens only if we get an all 0 equals B row. So that will happen if H is equal to 9, but K is not 6. B, a exclamation point solution. That means unique. That's what exclamation point means in math. A unique solution is going to happen if there are no free variables. So we need a pivot in each row. So H can't be 9. No conditions on K. So any K, you don't have to write down any K, but I'm just pointing it out here. If K, as long as H is not 9, K could be 6. That's fine. It would just mean X2 is 0. 0 is a fine number. But if K is not 6, then you're just going to have to solve for X2, but X2 will not be free. So C, infinitely many solutions, you need a free variable. So that means H has to be 9. H has to be 9 so that you don't get a pivot here. If H is 9, then to make this consistent, you also need K is 6. Okay, so it's worth it to take some time, pause, and study that example very carefully. All right, last one I'm going to do alone, and then you've got some practice problems for home, and there's a lot of them, but it's really important that you do them because it's really going to test your understanding. You know, you're going to do a problem just like we did here, and then also this parametric form and parametric vector form, you need to be able to do that. Okay, so this last example we're going to do together, there are 2 questions for each matrix. Is it consistent? Is the linear system consistent? And if so, is the solution unique? Triangle means a non-zero number. So this is an augmented system. And so I've got a pivot here and a pivot here. And so I can't get a bad row of all zeros and then something non-zero because triangle is non-zero. So yes, consistent. Is the solution unique? There are 2 variables, x1 and x2. Each variable corresponds to a pivot column, so there are no free variables. So yes, unique. Yes to both. Next one, pivot, pivot, pivot. So I've got a pivot in every row of the coefficient matrix, so I can't get an all zero equal B row. So yes, consistent. But no, not unique, because x2 is free. So there's a free variable. All right, and that is the end of this section.